I'd like to welcome those of you that made it to, I'm sorry, go.
No, that's okay. I was just wondering which side the screen was on. Is it on this side?
No, other side.
Okay, thank you. I'm gonna get my laser pointer.
I can be your proxy laser pointer, no problem. I'd like to welcome everybody to, this is the second in our virtual lecture series for the Big Bear Valley Astronomical Society. I'm very pleased and indebted to have Don Jennings to agree to be our speaker tonight. Don grew up not too far from here. He grew up in Kingman, Arizona, as I recall.
Needles.
Needles? Oh.
Needles, even more infamous.
Okay, I thought it was Kingman. Okay, sorry about that. He attended Northern Arizona State University before going
Northern Arizona University.
That's different than state? There's a difference?
Yes, it's different. I think maybe at one time it was called a state college, but now a couple of years before I started in Flagstaff, it turned to Northern Arizona University.
Oh, okay. Sorry about that. Okay.
No apologies necessary.
Needles and Northern Arizona University.
Yeah.
Oh, that's right.
Slow start.
NAU. That sounds right. I've heard that.
Yeah.
Before going on for his PhD, hopefully I get this right, University of Tennessee.
That's right.
In physics. Don has spent his career as an infrared, planetary, and occasional solar astronomer at the NASA Goddard Space Flight Center. Don's got to have the coolest job title I've ever seen. It's Space Scientist. Better than that, Space Scientist at the Laboratory for Extraterrestrial Physics.
Wow, well, you're reading an old document.
They don't call it that anymore? That's what it still says on your bio page, Don.
Does it really?
Yeah.
Did you get that off the Goddard website?
I think so, yeah.
No, they should know.
Planetary Systems branch, by the way. The title of Don's talk, as you can see up on the screen, is Observing Saturn and its Moons at Infrared Wavelengths from Cassini. Please welcome to our monitor, Dr. Don Jennings.
Here you go.
Glad to be here. That looks like a wonderful place where you are there. Is it still light outside?
Yeah, it is. Yeah. You can see that light streaming in through the door. That's ambient. The sun will be up for about another hour here.
Yeah, it's dark here, but okay. So on the screen, I think you have the first slide, which should be the ones that says observing Saturn and its moons at infrared wavelengths. Is that right?
Yep.
Okay. What I'm going to do is just kind of go through an overview of the Cassini mission, and I will, of course, try to highlight the things that I've been working on. But what I do is infrared astronomy, and so what I work on at Cassini is a composite infrared spectrometer, which you'll see referred to as CIRS, C-I-R-S, quite often during the talk. Composite infrared spectrometer. It's a Fourier transform spectrometer, which, if any of you are familiar with Fourier transform or FTIR, yes, you are? Okay.
Heard of it.
It's a type of spectrometer where we bring the light in, you split it into two parts somehow, you run them two beams through unequal paths and bring it back together, and by scanning the difference between the two path lengths, you can get the light to interfere with itself. And so you get what would be a Fourier transform of a spectrum. So when you do the inverse Fourier transform, or the Fourier transform, you get a spectrum. So everything I'll be showing in the infrared will come from spectra taken that way. So let's go to the second slide, slide number 2, which should be a double panel showing on the right. Yes. So on the right is Cassini sitting in an assembly room down at in Florida. It was actually Cape Kennedy side. It was on the Kennedy side, not the Canaveral side, where we were putting the instruments onto the spacecraft before it was placed on top of a Titan rocket that was launched in October 1997. And so you can kind of see, there's nobody standing in that picture, but you can see the ladder in that picture, give you an idea of how big this spacecraft is. It was kind of the last and very large spacecrafts, planetary spacecraft that was built before they started doing much smaller spacecraft. As I said, it was launched in 1997. We first started developing it in the early 80s. Scientists start putting together an idea for mission. The main idea for this mission was to drop a probe into the atmosphere of Titan, and hopefully it would land on the surface. People thought the surface might be liquid methane or ethane, and so they weren't sure whether the probe would just sink or what would happen. I'll show you some images and data that came from that probe later, but the probe, the Huygens probe, was developed by the European Space Agency, successfully landed on the surface and operated for about half an hour, I believe. And you can see it, since I can't point to this, if you look at where the little arrow says Sears on the Society spacecraft, if you look directly across from it, you see something that looks like a very large frisbee on its side. It's kind of on the left of the black area there. That's the Huygens probe pointing out the side. That was after inserting into orbit at Saturn. That was spun up and sent on its way, and it found its way to the atmosphere of Titan and then dropped it to the surface. It's kind of amazing when you think that there was no control of that. It was just pointed in the direction that they calculated, spun up, let go, and it ended up at exactly the right place on Titan, which was about a month, at least a month later, something like a month later. On the left panel is our instrument, composite infrared spectrometer, Sears, and that, to give you an idea, the circular thing on the left is what's marked 80K cooler is 40 centimeters in diameter. It's got a protection sock over the shower cap over it there. And there's a circle kind of looking away from you called the telescope. It's labeled telescope, and that's a telescope. It's 50 centimeters in diameter. That gives you an idea of the size of this thing. We don't really build instruments that big anymore. Having a large spacecraft allows you to fly big instruments. And those of you who do spectroscopy know that most of the time, in order to get high resolution, you have to have a big instrument because you need long path lengths somehow. That's not the case with all instruments, but generally speaking. And in that picture, you can see a couple of there's something labeled electronic assembly. That's the black box underneath the pallet there that the instrument's mounted on. And then there's a couple of star trackers pointing off to the left there. Let's go to the next slide. And this one is a comparison of all the instruments that are on Cassini. You can see the wavelength scale, kind of in a log scale at the bottom, spectral range going from a hundredth of a micron out to 1,000 microns. The instruments, the various types of instruments that we have on Cassini are ultraviolet imaging spectrograph, narrow and wide angle cameras, visible and near infrared mapping spectrometer, and then the composite infrared spectrometer. The Sears covers the longest wavelengths. You can also see it covers the largest range, even in fractional range. In other words, there's no way to look at this picture without saying that it's covering the largest in decades. It covers over 2 orders of magnitude in wavelength. The other instruments don't do that. Not really bragging. In order to do that, we had to go to some trouble because the instrument's actually 3 instruments. It's 2 interferometers to get the full coverage, and then one of them has 2 focal planes. The total coverage is, if you're interested in microns, it's like 7 microns out to 1,000, or if you're interested in wave numbers, 1,000 microns is a millimeter. If you're interested in wave numbers, which some of you might be, that's number of wavelengths per centimeter, which is the way we usually think about it and the way you're going to see it marked in all the spectra I show you. That goes from about 10 wave numbers out to 1,500 wave numbers. Just trying to impress you with my ability with numbers here. We go to the next slide. After launch in 1997, Cassini first went past, well, it flew around the inner solar system for a while. It swung around the Earth, and it swung around Venus, and finally it got slung out towards Jupiter. And being launched in 1997, it still didn't get to Jupiter till late 2000. October 2000, we got our first spectrum of Jupiter, and it left the Jupiter system in March 2001. And it didn't get particularly close. All we were trying to do there was use Jupiter as a slingshot, gravitational assist, to get a little more speed. But with the fine imaging we had on board, we still got some great data. You might remember that Galileo was out at Jupiter at about the same time. And of course, in our one little flyby, we collected many, many more times a day than they did. They had a problem with their antenna, if you remember, and it didn't unfold, so they were sending everything back at a low rate. We collected a lot of data at Jupiter. In the next slide, you can see an example of the type of data we take with the composite infrared spectrometer. I put this together from all three focal planes, so it covers the whole range of the spectrometer. In this picture, in this spectrum, you can see ammonia on the left there, low wave numbers between like 0 and 200. Then there are these two big dips. Those are caused by hydrogen in the atmosphere, which is the most abundant thing in Jupiter or Saturn's atmosphere. The hydrogen colliding with itself.
Don, for those of us who don't remember wave number very well, could you sort of give a rough micron scale for that?
Yeah, this is going from on the left, we started about 1,000 microns, 1 millimeter. And on the right, which is the shortest wavelength, it's at around 7 microns. So, is that sort of what you meant?
Yeah, it's been long enough for me, and I'm sure there's several in the audience here who are not familiar with wave number.
We, spectroscopists, at least high-resolution spectroscopists, usually use wave number. It's kind of more physical because it's spreading. You're talking about things being spread out in energy when you talk about spread out in wave number. In frequency, wave number is a frequency. So if you do it in wavelength, then it makes the infrared part of the spectrum look bigger, but it squishes things around, and we don't like to do that. So when you look at a spectrum like this, I'll just talk to you a little bit about why we do it like this. When you look at a spectrum like this, the lines are kind of evenly spaced through here. You can see they look like regular. If you did that in wavelength, they wouldn't be regularly spaced. And that's kind of non-realistic because nature kind of spreads things out in energy. The wavelength comes from the way that it was originally measured. I'm a little prejudiced there, but you get used to going back and forth. You can see there's ammonia, there's hydrogen I was talking about, and then the C2H2 is acetylene. We see that in almost everything we look at. There's a ethane, which is also around the outer solar system quite a bit. Ammonia appears in Jupiter, but strangely enough, you can't see it when you get to Saturn, even though the rest of the spectrum looks similar, as you'll see in a minute. The reason is that Jupiter's warmer, so ammonia can exist in the gaseous state in the atmosphere, whereas you get to the outer solar system and it tends to get frozen out. Other things that are not frozen out appear in that range. And then there's methane. Methane is very important to us because we use it as a thermometer of the atmosphere. We assume that methane is, that the same amount of methane everywhere in altitude, everywhere on latitude and longitude, same relative amount. And then because we can assume that, we think we can assume it, We then can use that to derive the temperature by looking at the shape of the spectrum. I'll show you some examples of that in a minute too. Okay, we'll go to the next. If you take the previous data like was on the previous slide and you pick out certain wavelengths or wave numbers, you can make them correspond, because of where those peaks were, you can make them correspond to different material in Jupiter's atmosphere. And so here you see it color-coded. Blue is acetylene, which is that carbon, your 2 carbons, 2 hydrogens. Green is methane. And then what we call a hydrogen continuum, which was really part of those 2 dips that I was talking about. We call it continuum, but it's really big fat lines in the spectrum. They probe different altitudes in the atmosphere. Hydrogen tends to be lower. Acetylene tends to be highest. They also, as you can see, highlight a lot of structure. So this is a picture of Jupiter taken in the infrared by looking at molecules in the atmosphere. That's basically what this is. There's some, besides the band structure that you would expect to see, there's some really interesting things going on at the pole. You notice that acetylene, which probes the highest altitudes in the atmosphere, has these bright spots at the pole. You can see them kind of offset from the pole there. And right at the pole, we don't get data, but at least not enough to put on this plot. But you can see those blue splotches both in the south, which is on the lower left, and in the north, which is in the lower right. And those are due to hot spots in the atmosphere near the pole. They are coincident with the magnetic field, and energy is being dumped into those regions along magnetic fields. Particles coming off of the moons, actually, ions and such coming off the moons will follow the magnetic field lines down into the atmosphere and actually heat up the atmosphere there. So there's a lot that goes on there. We see aurora in those locations, and we think that the variation is in step with the solar cycle, although it's pretty hard to correlate that a solar event, you know, like a coronal mass ejection, particular event like that, with any particular event on Jupiter. There seems to be more activity during solar maximum. Next slide. So I was telling you that we could measure the temperatures using methane, and this is an example of that. You see on the bottom you have 60-degree north latitude on the left and 60-degree south latitude on the right, and then the altitude, which we always plot as pressure. That's the way we do it. So pressure is, the altitude is lowest on the left and highest on lowest on the bottom and highest on the top. You can see how the temperatures vary. Just roughly speaking, you have pretty hot temperatures up high, and then as you go down to middle region and then lower, they go to low temperatures and then they come back up. That's just your typical temperature inversion that we see in atmosphere so often. So it's hotter up high, and then you go through a minimum at some lower altitude, and then it actually starts to increase again. Next slide. We'll just run through some pictures now of Saturn. So in 2004, July, Socitey went into orbit around Saturn. That was a nail-biting experience because it actually went inside some of the rings in order to go into orbit. You're never quite sure what you're going to find when you do that. But after about a 90-minute burn, it went into an orbit that was then refined over the next couple of orbits to aim it so that it could drop that probe into Titan. And then after that, for many, many orbits now, that's up around 100, we've been just orbiting in all kinds of inclinations, and every time we fly past Titan, we do it at a slightly different place. With the gravity of Titan, we'll pull the orbit into a different inclination, and so we can scan north and south latitudes, and then go back to the equator and scan the equator. We have a lot of control that way. This is a picture looking from underneath it when during early mission, the rings were tilted high so that the southern hemisphere, the south pole of Saturn, was in sunlight. We've actually watched it go from that to the north being in sunlight now. Cassini mission is so long, and have watched the seasons change. I'll show you some effects of that. We can go to the next slide. looking down from the top. Kind of a similar picture, but in this case, it's later in the mission, and this is the North Pole, which is now in sunlight. If you look closely, you can see there's a shape to the ring at the pole. It doesn't look like a real circular ring. I'll show you that, more of that in a minute. So you can see we get orbits that are not only kind of equatorial, but also polar. And we just crank them around. It's a slow process. It takes a year or two to move it over the whole range. But we've been at Saturn since 2004, so we have plenty of time to do this kind of thing.
Are these colors pretty much real colors?
I'd say yes, they are. I mean, we got spoiled by Voyager. They always used to enhance their colors. And I asked a guy once who was studying the real colors, and he's trying to calibrate the Voyager images that had all those bright things. I said, "What does it really look like?" He said, "Well, if you look at Saturn or Jupiter through a telescope, that's what it looks like." If you think about it, there's nothing in the telescope really that changes the color.
Yeah, my telescope though, I don't see blue at the pole.
Right. Well, yeah, we don't see the poles at all. It's subtle, but I think this is pretty realistic here.
Very cool.
Another nice image of the shadow ring, the shadows of the rings falling in the southern hemisphere. It's and you can see there's a change in color here. I saw an explanation for that. I'm trying to see if I can remember what it was. There's actually a difference in the haze in the south, just because of the way the illumination has been occurring before this. So you get more sunlight up near the equator, and it's less haze. So down near the South Pole, you get more haze and it's grayer. I just show this because it's such a pretty picture. And then another one like that. Here you have the rings. You're looking along the ring plane towards the shadow of the rings on Saturn, and there's Mimas over there.
Okay, we need to catch up with you. Hold on. Okay.
Pardon?
Slide 10, is that where we are?
We fell behind you on.
Oh, sorry, I'm on number 11.
Okay, sorry about that.
How far back were you?
We were still on the 9 that was looking from above.
That's my fault for forgetting to tell you.
Okay, we're up with you now. Continue on. Thanks.
So you saw 10. Did you spend any time on 10?
Not much. We can go. We're back on it now.
Okay, I just want you to be able to take a look at that. This is really nice. This is the shadow of the rings hitting in the southern hemisphere, and then the haze I was talking about is that grayish color near the south there. You can see it's a different color than up around the equator. Okay, next slide. And this is what I was just talking about with you're looking along the rings here towards Saturn, and the shadows, ring shadows are on Saturn. And there's Mimas over there on the right.
Wow.
Okay, next. Should be on 12 now.
Yes.
Here you can really see the hexagon on the north. And there's also some nice little structures outside the hexagon, more circular, but they start to look a little bit like Jupiter. We're not used to Saturn having this kind of structure in its atmosphere. Jupiter's the one that usually has it. Saturn's just out further, it's colder, and usually it looks more bland, but if you look closely like here, you can really see that it has the same kind of structure. In the north, the hexagon shape, it seems like that's just not physical at all, but in fact, if you think about it as a wave going in a circle, you can kind of imagine that you could make this happen. So there's something about the combination of the speed of the winds up there and speed of rotation, and how often this material has to catch up with itself, and the wave structure, and it'll just hits its resonance where it has this shape.
Wow.
Why it's a hexagon? It just happens to be the shape that works there. If you look inside of it, the hexagon kind of breaks up. So right at that one spot, the hexagon works. That one radius hexagon works. There's a lot of work going into this. If you look inside the hexagon, or even just outside, you can see how many little swirls and spots there are. It's quite complex. And then outside of that, you have a modeled ring pattern reaching out to this kind of a white area. And I'm going to show you something that's going on out there, or has been the last few years. And then it gets kind of bland further away than that. So this is the North Pole. I remember I showed you at the beginning when we had the South Pole in the sunlight. So now we have the North Pole in the sunlight. We've gone through that complete cycle of seasons from northern winter to northern summer. Next slide. Should be number 13.
That's where we are.
And this is the southern hemisphere. When we first got to Saturn, southern hemisphere was in sunlight, so it was the same kind of situation we just saw in the north. But here you don't see a hexagon. It may be because we arrived too late to see it, because it had already been southern summer for a while. But you can see that there's still a vortex down there. The spot, there's a couple of spots here that are interesting, but they're not what I'm talking about. I'm talking about in the center, low, there's kind of a bullseye pattern. I assume you're pointing at it. And that was extremely warm right there. When we got to Saturn, we looked at that southern spot region, and the temperature was so much higher than anywhere else. It really surprised us. Go to the next slide. I'll show you an example of that. Wait a minute. Not the next slide. Okay, I'll get to what I'm talking about in a minute. I thought it was the next slide, but it's not. Okay, the next slide is in 2010. I was just showing that there's structure in the north as we went into northern summer, and it's actually more like northern spring. It's not really summer because we haven't reached the extreme of the tilt of the axis towards the sun yet at the solstice. Solstice isn't until 2017 actually. But as the North Pole entered sunlight, things started happening in the north, like that hexagon. And one of the things that started was in 2010, this storm all of a sudden erupted at about 30 or 40 degrees north latitude. And over a period of a few months, it wrapped itself completely around the planet. In the visible, it was a remarkable object. Hadn't seen anything like that. Turns out when people went back and looked at earlier photographs of Saturn, they found that things like this had happened before. But because Cassini was there looking at it up close, it was much more dramatic than anything we'd seen before. In the infrared, when we looked at this, it turns out some of the hottest gases in the stratosphere that we'd ever seen were in this region. Right near the head of the storm, sort of in this blue area near the yellow part of the blue box, sort of in that region there. Some of the temperatures got up to around 200 degrees or higher Kelvin, which is really hot for us. Typical atmospheric temperatures on Saturn are like 130, 140 degrees. This was so hot that we saw gases just brighten up in their emission, just turn on. We call this a beacon. And in particular, one gas, ethylene, had really never been seen on Saturn before, and all of a sudden it was brighter than anything we'd ever seen on Jupiter. And it was remarkable, and it kept going. That kept going for several months. We still are seeing remnants of it a couple of years later. Okay, next slide. Should be number.
Spectrum.
Well, it doesn't have a number, but it's a spectrum, right? Yeah, that's right. This is a Saturn spectrum. Again, just as I mentioned before, ammonia, which we had seen in the Jupiter spectrum, is gone here. In its place is phosphine, which is a similar type of molecule with the nitrogen replaced by phosphorus. But there's no ammonia in here. It's all frozen out. Saturn is too cold. You still see these two big dips due to the hydrogen collisions in the atmosphere, and there's the acetylene and ethane and methane again. It's a similar type spectrum, but subtly different. Go to the next slide. When I say similar to Jupiter, but subtly different, I should say. You know, the next slide. When I was talking of this, I should have put this slide earlier when I was talking about the South Pole. But you can see here, this is an infrared image showing that same thing at the South Pole. See that bright spot right at the South Pole in the upper image? Mm-hmm. That was taken from a ground-based telescope. That was taken from a telescope in Hawaii, in Mauna Kea. But from our instrument on Cassini, you can see the spectra that we saw in this region, which includes acetylene and ethane. And see how the one marked south pole sticks up so much higher than the others? As we moved our field of view towards the south pole, the whole spectrum just lit up. So that little tiny region that looked like a bullseye was very hot. The reasons for this are, the atmosphere has got a circulation pattern, and during one season, the gases are flowing from the equator to the north, or in this case the south, and dumping material there, and also heat. And so you have more gas, more of some of these constituents, and you have a hotter temperature. Then of course the seasons switch and everything flips, and the same thing happens then in the north. Let's go to the next slide. We'll talk about the rings for a minute. This is just a picture, a nice picture showing the rings. So much structure and detail in here. We go to the next one. I've tried to show what the different wavelengths look like, what the rings look at different wavelengths. So in the ultraviolet over on the right, for instance, the red is a dirty material, and the blue is more pristine, icy material. And so, for instance, in the gaps, that little narrow inky gap, you can see there's actually some dirty, fine material in there. It's lit up red, even though it looks, in the visible and all the other wavelengths, it looks like a gap. And in the UV, you see there's a big band of fairly pristine material, and then it gets kind of dirty again in the inner part near the Cassini gap. Now, if you go to the infrared, you can see the same kind of thing, but here it's coded in temperature. So red is the hottest temperature here, and blue is the lowest. Red is about 110 degrees, and blue is about 70 degrees Kelvin. So you can see how the temperature varies over this material. And then if you go to the radio is really looking at sizes. So purple is the large particles bigger than, say, 5 centimeters diameter, and then in green and blue, this greenish area is smaller particles. And where it's very bright, where that white area is where the ring is not only large particles, but it's just opaque. In that region, this was done with a radio occultation with a Cassini flying behind Saturn, and looking at signal coming from the Earth. It just didn't make it through where those white areas were. And in the visible, that's pretty much what I've been showing in all the pictures. So you can see how much information there is in there if you can look at different wavelengths. Next slide. Just another view of the ring. One thing that we should keep in mind is, it's always been an enigma, these rings. Why are they only in Saturn? Well, it turns out they're not only in Saturn. What keeps them so fluffy, so big on Saturn? I mean, they're really thin, but they're so huge in width. Well, we get close and we find out that it's got these little moons that are orbiting in these gaps, and kind of shepherding the rings. We also find sometimes that the material is being traded. We like to think that those moons are somehow making the rings do what they do, but of course the real picture is that it's a coupled system. The rings are also interacting with the material. Stuff's probably coming off the moons into the rings and vice versa, but it's very complex. This picture doesn't show, but sometimes you see wave structures in the rings where it gets to have some kind of a resonant pattern, like spokes on a wheel. But you can see these two little moons.
There does appear to be some sort of structure near the moon over on the outer ring there. A couple of dark bands coming in like spokes, and discontinuity by the ring next to it, way over on the right there.
Yeah, I see what you mean, and I'm pretty sure that is real, but I won't swear to it. But definitely where that moon is, there are waves and stuff. So there's one that looks a little odd to me, but the others are, certainly you're correct, the others are wave structure, and that one probably is too. Yeah. And also, is there a shadow, if you look down near the center of the ring, is it kind of a shadowy structure, or this spoke shaped, or is that can you see that? Maybe you can't see that. I won't dwell on that, you probably can't see it. It's pretty subtle in my picture. Anyway, so there's a lot of structure. You get radial structures, you know, circumstructures and so forth. So anyway, the rings are pretty cool. Some people spend their whole life studying the rings. For the Cassini infrared spectrometer, for the composite infrared spectrometer, however, the rings have almost no signal. There are people using our spectrometer to study the rings, but there's so little signal there that people looking at the atmosphere sometimes use the ring spectra as a reference, zero reference. The people doing rings in the infrared really have a hard job. There's not much signal coming from the rings, but they do get a lot of results. I don't know, did you hear about this last summer? There was a day where they organized us all on Earth. We were supposed to go outside and wave at a particular time, remember?
Yeah.
Yeah. I think it was cloudy where I was. But in this picture, this picture was taken with the sun in occultation. I mean, every so often we have a geometry where you can look towards the sun because it's not in the picture, right? Just like a solar eclipse. And so taking advantage of that, they were able to take this photograph and show how much structure there is even outside the rings. You see that H structure? And also, even though you can't really see them here, this picture does have Mars, Venus, Earth, and Moon in it. If you blow it up, you can go to the website, find this picture, blow it up, and you'll see these planets. And on Earth there's a whole bunch of people waving. And I can't blow it up enough to see that.
Dr. Jennings,
Anyway.
the little moon in the center vacancy there, did it come from that ring? Did it accrete from there?
Wait a minute, are we looking at the right picture? What picture
19?
are you on?
We're on slide 19.
Oh my gosh, I'm sorry.
Oops.
I just did a lot of talking for nothing.
Uh-oh.
Say it again, what was your question?
On slide 19, the little moon that's about just to the left half there in that ring, did that accrete from that ring, do you think?
Is it a piece from the ring?
Did it come from that ring? Did it gather debris?
Did it accrete out of the ring?
Yeah, I'm not an expert in this, but I think that it's a process of not only accretion from the ring, but exchanging with the ring. So it's a body that may just be a larger ring particle.
Yes.
And then, I forgot, okay. Any more questions about that slide? Because I spent a lot of time talking about the next slide without telling you.
Oops.
Yeah, this one.
Oh,
So when I was talking about July 19th, this is what I was talking about. I'll run through it again. The sun is behind Saturn, so it's like a solar eclipse, so we'll point at the sun without having it saturate or cook our cameras. And you can see how much structure there is around Saturn that doesn't occur in the visible rings themselves, that you see in forward scattering. So there's a lot of stuff around Saturn that you don't normally see in the pictures. And in this picture, which you can get on the web, if you blow it up, you'll be able to see Mars, Venus, Earth, and Moon. And on the Earth was, a few billion pointy-headed geeks waving.
We resemble that comment.
But it was cloudy where I was. Next slide, please.
Oh.
Yeah, right. That's the one. I'm going to just talk about the moons of Saturn a little bit here. So this is a thermal image of Phoebe. On the very left, it's just a radiance image. This is what the intensity of the infrared radiation looks like coming off. And if you convert that to temperature, you get the middle one. And you can see how that correlates with the visible image of Phoebe. So the part that's in sunlight tends to be the warmest, not too surprising. You can also pick out this huge crater, and maybe some other smaller craters in the infrared signature. Okay, next slide. And now this is showing 4 moons.
Holy cow.
And just what's amazing here is just how different the moons look. Tethys is kind of a normal looking place, but Dione has all of this structure on the surface. These are all pretty much icy surfaces. Mimas has this Death Star crater on it. People are always having fun with that. Very large impact, which somehow did not break Mimas in half. And then Iapetus has this what looks like a shadow across it. I'll show more of that in a minute. And also you can see the various diameters here. Now go to the next slide, which should be 23, right. There's Rhea. You can see a fresh crater among a bunch of older craters. This kind of looks familiar to us, right?
Yep.
It's a little bit like the moon or Mercury. Go to the next slide.
24.
This is Iapetus, right? 24.
Yes.
And this looks very different. Something has collected on the leading edge of Iapetus that has not just covered up the ice, which you see on the north here, but actually heated up the surface a little bit so that there's been a migration away from the equator. And you see the equator has a ridge around it? We're starting to see this now and then. This is the largest object I think that I've seen with a ridge around it, but some of the asteroids seem to be flattened or have ridges. You know, there are explanations for this. We don't really know, of course, why it happens. An explanation might be that there was a material orbiting it that fell to the surface. It might also be some just compression effect, but it is a very distinct ridge right at the equator. Kind of like a walnut. And then you see these large craters here also off to the side. Next slide, 25. Enceladus is one of the most interesting places in the Saturn system. And we thought Titan was going to steal the show, and it's done pretty well. But Enceladus turned out to have activity. You've probably heard a lot about it. This is almost a full picture of Enceladus. The part that isn't showing as much in the south is actually the most interesting part. But you see how you have different colors of ice here with craters, of course. Where you see craters, it usually means you're looking at older surface material. In the south, there's kind of these stripy looking things, and they're more bluish. And that means that this material is younger. If you go to the next slide, and I encourage you, by the way, to go to the web, to the JPL Cassini website and look at images, because all of these images, or most of these images, can be found there, and you can look at them a lot more closely. If you look at now, are you on slide 26?
26.
Yeah, so if you take that southern region that I just said had the blue ice on it, the scratches. This is what it looks like if you have the sun shining from the other side of it towards you. And these are plumes coming out of cracks in the surface. These plumes vary in time. They vary with the position in the orbit around Saturn, because something under the surface is being stirred up by the gravitational tidal effect on Enceladus. It's keeping some liquid under the surface that's spewing out of cracks on the surface that are also opening and closing tidally. And if you go to the next slide, which is 27, right?
But question.
Yep.
Like the Jovian moons, are Enceladus and the other larger moons, are they in harmonic orbits and resonance orbits with each other, or are they just being stirred up by the orbit around Saturn itself?
It's the gravitational effect of Saturn itself. So if you have a slightly eccentric orbit, you get a huge tidal effect on these moons. They are gravitationally locked, so they're of the same faces always towards Saturn. So that spinning was dissipated ages ago. But they're going closer and further away in their orbit, and that's causing a stretching and compression. But as far as one moon to the next, no, the moons that they don't know about each other pretty much, but a lot of material comes off of Enceladus, however, and ends up in the rings. We're starting to think that the rings, at least some of the rings, are mostly supplied by Enceladus. And the water that we see in the atmosphere of Titan, we think probably originated in Enceladus. This is spewing a lot of material out into the space there. So it's turned out to be a very important body. And of course, there's speculation about if there's water, liquid water under the surface, the usual speculation about whether there could be life there. That Cassini has not seen yet. Next slide. And so here's another view that's taken from the infrared, taken in the infrared, and you can see on the left what we expected the temperature field to look like on Enceladus. You know, it'd be hotter on the side facing the sun and so forth, but we didn't think anything unusual would be happening at the poles. You can see what we actually observed in the center there, was very, very bright and hit the lower pole. The temperatures can get up around 170 Kelvin, whereas Enceladus is probably more like 80 Kelvin most of the time, most of the surface. So it's a huge change, and the material coming out is very, very high temperature. And the surface around where these plumes come out is also warm. So this is just a general region of elevated temperature. And if you go to the next slide, I probably should have made it clear that composite infrared spectrometer is really measuring thermal emission. The other instruments are looking at reflected sunlight or something. What we do is look at the heat coming off of the object. Everything we see is heat coming off the object. So we can look at, on the night side, for instance, when we're looking at this emission here, it's not reflected sunlight. This is heat coming off of those cracks at the south side of Enceladus. If you can see the visible image there in gray, and these stripes, which we call tiger stripes, lay right over these big cracks in the surface. Can you tell that?
Yeah, yeah.
Yeah, they just track right along. And the general region in which you see these stripes, you know, is kind of confined to within 70 degrees south, you know, 70 to 90 degrees south. That general region it tends to be warmer, and there's probably a reservoir under there, maybe a couple 100 kilometers down. I kind of think it's closer to the surface than that, but I'm not an expert in that field. But if you can make a rough calculation that if the material underneath had to be liquid, had to be some temperature to be liquid, and the surface is a certain temperature, how far down is that if it's pure ice? And it turns out to be, you know, 100 kilometer-ish. Anyway, you can also see a scale here to give you an idea how large a region you're looking at. Some of these flybys that Cassini took at the South Pole of Enceladus came within 25 kilometers of the surface.
Wow.
Now I'll talk about Titan for the rest of the talk, which I guess is about 10 more minutes. And this is how, on the left is what Titan normally looks like. It's what Voyager saw, kind of an orange haze. Couldn't see the surface. One of the reasons we went back to Titan and dropped a probe in is we wanted to see what the surface looked like. But the camera was also, the visible camera, it's not really visible, the near-infrared portion of the camera had a filter where they expected to be able to look through the haze absorption bands and see some of the surface. And so on the right you're seeing some imaging of the surface taken with the imaging camera. Next slide, which should be 30. If you do that over and over again, you can build up an image of what the surface looks like. This is a kind of a Mercator projection, and especially around the equator, you see these dark regions surrounded by lighter regions, and there's a very bright, very large, bright white region over at about 120 degrees. You see there, we call that Xanadu. That's a kind of an unexplainable feature at the moment. We don't know. It's on the leading edge of Titan. It may represent some event in the past, but so far we don't know what it is. It has unusual, it looks high there, but it's actually low. In the darker regions in here, you have, especially around the equator, you have sand dunes. Let's see if I can get to some pictures of that in a minute. Let's go to the next slide, which is number 31, is that right?
31, yes.
So I'll mention also that there's some indication, this image was taken in the near infrared, with the near infrared imaging spectrometer VIMS. there's some indication that there's material coming out from beneath the surface of Titan. It's called a cryovolcano. We think that Titan's atmosphere, it shouldn't be there. Titan's atmosphere should have collapsed, after 50 million years. So, but Titan's been around for a billion years, 4 billion years or whatever. So, how do you explain it has an atmosphere? Well, we think it may be replenished from under the surface and placed through things like cryovolcanoes that maybe are spewing out material into the atmosphere, which keep the methane in the atmosphere. If it needs methane, and the methane is the one thing that goes away the quickest. So maybe cryovolcanoes supply it. Next slide. This is a radar image of a couple of craters. These are not volcanic craters, probably impact craters, and you can see the difference between a young and an old crater here. The newer crater on the left just shows more structure, and the one on the right is more eroded. I'm just showing this so that you can see what crater things look like, especially in the radio. We do a lot of our imaging in the radio because the radio goes through the atmosphere with the haze in the atmosphere with no problem on Titan. Next slide. One of the things that we expected to see when we went to Titan was lots of liquid on the surface because of this same thing. There's methane in the atmosphere. We think the atmosphere has been around for billions of years. The methane that was destroyed should have turned into ethane or it should have condensed out. Methane might have condensed out, but we expected there to be a lot of condensed stuff on the surface, mostly methane and ethane. It didn't turn out to be all that much. That's been a big puzzle. But we do have big lakes of liquid near the pole, and that's what these dark areas are in this picture. This is looking down at the North Pole of Titan using radio maps. These large bodies of methane or ethane are called mares. There's a Kraken mare you can't really probably make out, and a Legia mare. And we're getting a lot of information on the depth of these things and looking for changes with season. The lakes are a big object of study on Titan. Next slide. From an atmospheric standpoint, so this should be slide 34. From an atmospheric standpoint, the haze is very interesting because photo association of molecules in the upper atmosphere cause the haze, and of course those molecules are things that we look at with our infrared spectrometer. We also can see the haze itself. You can see that there's an orangish haze. It reaches up to like 200 or 300 kilometers above the surface, and then above that, up at about 500 kilometers, there's the thinner haze. This goes around the whole globe, but if you look on, take another look at that more closely on the next slide, slide 35, you see that those hazes are also divided into lots of layers. There's a lot of structure there. And if you go to the next slide,
36.
this slide, says Cassini ISS at the bottom, right?
Yes.
Okay. This is showing what the haze looks like globally. Besides that haze that I was just showing that's over the whole globe, the poles, you have these hoods that form. I'm cheating a little bit here because until recently there was only a polar hood in the north. We had always gone to Titan. Voyager and Cassini had been to Titan when the north was in winter, and there was a much thicker haze in the winter. It's like when things got colder up there, they condensed more, there was more material there. There were some molecules in the gas phase that we only saw in the north, nitriles in particular. But recently, something started forming at the south. The south is now coming into the night time, as you can see there, and there's this white spot in the southern hemisphere at South Pole. Can you see it there?
Mm-hmm.
You can call it a vortex. Yeah, I think you're pointing at it. It's actually high enough that it's sticking above the shadow. Can you tell that in that picture, that it's still in sunlight even though the terminator, the shadow is closer to the left? So this thing is a very high cloud that's been forming from material that's collecting in the south now that it's going into southern winter. There's just two views of it here, a year or so apart. Next slide. Spectrum of Titan. Now Titan is my favorite place. You can see that it has like 5 times more molecules and much more complex ones than you saw in either of the other places. Titan has got a nitrogen atmosphere. You can see nitrogen is called out over on the left there. It's got a lot of methane. You see the methane over on the right. And it's got the acetylene and the ethane again, just like Jupiter and Saturn. But here you've got these other things. Hydrogen cyanide, cyanoacetylene, diacetylene. It's a petroleum engineer's dream, I think. And you can see how much information is in a spectrum like this. I mean, every little feature in there is telling you something about the atmosphere, about the material in the atmosphere and the atmosphere itself. It's telling you temperatures, the amount of that material. Maybe you'll be able to get some winds, because if you know the temperature field, you know how the atmosphere that has to be moving. There's a feature over here that's labeled ice cloud. That's a condensed feature. We actually don't know what the material is, but we've seen it ever since Voyager. It's very prominent, and it changes dramatically with the seasons. So there's a lot of information in the spectrum of Titan or anybody, any object that has an atmosphere. And the next slide.
38.
This is getting to some things that I've been working on more recently. So this is a measurement that we can make with this instrument of the surface temperature, because there's a window in the spectrum at 19 microns. You couldn't make it out in the previous slide, but there's a place there where you can actually see the surface. And we can measure the temperature of the surface. You can see here that near the equator it's high, it's around 94 degrees Kelvin, and it dips off a couple of degrees towards the poles. It has also been shifting. This curve was done early in the mission, and by now it's the low side is now in the south, which is on the left here, and the high side is in the north. So that shifts with season. Go to the next slide. Now this one is the one that shows Titan's southern polar vortex. Is that right?
Yes.
That's what you have? Okay. There's another view of that vortex I was talking about. Here you're looking head on, and this one was taken just last year. You can see how it is above the shadow. You see how the terminator there is very distinct, but this thing is sitting back of that terminator. The sun is on the right here. That is a close-up shot of what that looks like over here from 2012 when it was first forming. And in the infrared, you can see the way they were looking with VIMS in 2012 in the lower right. You can see that it showed up as a little patch just off the limb. Next slide. So recently what I've been doing is following that spectrum that was marked, that feature that was marked ice cloud in that spectrum. It turns out that this, down around the South Pole now, that the emission has formed this ring morphology, I call it collar, where it peaks up in a ring about 10 degrees from the pole itself. And we only have slices through the pole, so I can't show you the whole map. I'll show you something similar to that in a minute. But you can tell that this is a sweep of our field of view, and as we swept through, that feature that was marked ice cloud peaked up, dipped at the pole, and then peaked again, and then went back down. So this the strong structure, this seems to be expanding with time. We'll have to keep watching it, but it's spreading out. And it also does something really odd. If you look closely, it's shifted slightly from the pole itself. And that turns out to be an odd thing about Titan, that the atmosphere is tilted 4 degrees from the axis of rotation. Go to the next slide. If you look at the temperature at the South Pole, the same kind of thing occurs. And you're kind of seeing, this is a deep temperature well at the south. This is not a collar, but this is the temperature dropping off as you go to the South Pole, and forming this deep well, which is blue, and it's shifted by that same 4 degrees. And sorry that it doesn't say sun properly there. I hope, does it look better on your slide? No?
Oh.
Does it say SU above and N below?
Yeah, I didn't correct that,
Okay.
sorry.
I don't know why that happened. Sorry, Cloud. Anyway, go to the next slide. And this one says HC3N at South Pole.
Yes.
Okay, so now we're looking at a nitrile, complex nitrile at the South Pole. You see the ring? You can see the ring structure there, but in the center of the ring is a peak. I call this a sombrero shape. So it has the same ring structure that the ice cloud did, but now this is a gas. And the gas is doing something different because in the center, near the pole, it's peaked again. So it shows an even more complex structure than the ice does. We don't understand this yet at all. All we can do right now is follow this and try to figure out, how it's changing, how it's behaving. It's easier for us to understand what the gases are doing because we know what they are. The ice cloud, we don't know what the material is. But this is something that we're going to have to try to follow best we can and hope that we can see it progress completely before the end of the Cassini mission, which is only a few years away. It's supposed to end in 2017. Let's just hope that we have enough information about all these crazy things that are going on in the south before the mission ends. Okay, next slide, getting close to the end here. Just to remind you about temperature fields. So it's like that temperature field that I just showed that dipped at the South Pole. I mean, we can make those kind of maps in latitude and altitude during the whole mission. And you can see here that this is something from the beginning of the mission where it was, again, hot up high, dips down, gets cold, and then below this, where we can't see it, it actually gets warmer again. So we're looking at just pretty much the stratosphere here. You see the temperature structure. So in the north, in northern winter, we had a very cold place lower down and a little warmer up above, and that's been changing with season. And just some pictures now. The Huygens probe was dropped in January 2005. And as it went down, we started seeing these things that look not only very alien, but very familiar. So now I'm on slide 44. It kind of looks like a coastline with rivers flowing into an ocean. But of course, the ocean is a solid surface. It may have been more liquid at one time, and there had to have been a lot of liquid flowing on the surface to form this. We've seen some rain, we think, and some clouds, but we haven't seen the huge storms that must have caused this. So something happened in Titan's past. Maybe we'll see it again before the end of the mission. But here's another view on the next slide, 45. This looks like the coastline of California to me. It's only almost make out Santa Barbara there, It looks very familiar. But again, it's completely different material. The surface is solid. Rocks on the surface here are blocks of ice, water ice. I mean, water would just be like a rock on Titan. Temperatures are around less than 100 degrees on the surface. Again, it's not liquid, it's not a coastline. That's a flat area, but it's not water. Next slide is just showing a kind of panoramic view that the Huygens probe took on its descent. And it's putting together pictures of the surface in the area where the probe went down. So some of the things that I just showed you occur in this picture around the edges. You can see that the Huygens probe landed in the center here pretty much. It's kind of a darker region, but all around it is all of these kind of like coastlines and things. We're getting a lot more information about those things now from the orbiter, but of course not as up close. And it's always important to land something on the surface. So you get a very good idea of what it looks like up close in one spot. It always makes you want to go back and look somewhere else, but still, you know a lot more than you did from orbit. The next slide, 47, is a swath of a radar pass. You see how much variation there is on the surface. I don't know exactly where this one was taken, but you can see all the different structures here. Maybe, again, channels where liquid was probably flowing at one time. And then the next slide. One of the most interesting things on Titan are the dude fields. With very regular patterns. It looks to me like somebody took a rake and just scraped the surface. Very, very long parallel lines. They're about, a kilometer high and a kilometer between them or something like that. They're pretty well separated, but from space they look so regular. I don't know, I hope you can see that here.
Are these aligned equatorially, or are these aligned north-south, or?
Yeah, yeah, you're right. This picture's a little misleading. They are aligned along the equator. They're aligned along latitudes predominantly, but they do move around depending on obstacles. So you know that they were formed by winds because they come to an obstacle and they kind of disappear on one side or go around it. And they behave somewhat like the dunes we see on the Earth, although they're all longitudinal. On the Earth we tend to see dunes that are across the wind direction, but instead of Titan they're always along the wind direction. Taking a lot to explain that, there are longitudinal dunes on the Earth, so we think it's probably something similar to that. But the dunes we don't even know really what the dunes are made of. It's probably some of the material that's condensed out of the atmosphere. And the last slide then is number 49. Well, it's not really the last, but it's the last picture. Is what Titan's surface looks like. So the Huygens probe landed on the surface. To their amazement and joy, it was still working. They got data on the surface. I think they kind of wish they had a panoramic camera at that point. They're being very conservative. They just had this one camera and they got this great shot. And if you look at this shot carefully, I don't know if you can here, the rocks up front near the lander, which they were calling a probe originally, and then of course after it landed, it was a lander. Those rocks are probably made of water ice. They're like boulders of water ice. And way in the distance, you can make out hill crests, like a horizon made of low-lying hills. It kind of looks like it's not that alien a place. It almost looks like it could be a picture from Mars or my backyard in Needles. I know I'm running a little long here, but let me just tell you what's going to happen in the next slide, what's going to happen in the rest of the mission. This is an overview of the Cassini mission, and you can the periods of time here, like the years. This is split up into columns, which are years. You can see how many passes we had of Titan each year, and it varied quite a bit. In 06, 07, we had quite a few passes of Titan. That's the yellow balls at the top. That's 22 passes. You can see the number of passes of Enceladus. Enceladus is shown as an orb with a little plume coming out of it, and then all the other moons at the bottom. You can also see the inclination of Saturn. So we went through equinox in 2009, and you can see the winged rings are edged on there. That's what that means. And then so it went from illuminating the southern hemisphere in Saturn to illuminating the northern hemisphere. The mission will end assuming that they keep our funding. The mission will end at the northern summer solstice, and we will have gone almost 1.5 year on Titan at that point. Almost covered a whole 1.5 year.
Wow.
That's remarkable when you think about it. When you think about Voyager going by, in one day, and we were able to have an outpost out there for decades, for a decade. And then at the very end of the mission, we're going to do some bonsais. We're going to do what are called proximal orbits, where we fly inside the rings, close to Saturn, and take data up close. And that's what all those little gold things are over on the right there. Those are orbits. We're going to fly very close inside the rings, take our chances, and in the last gasp, the spacecraft is going to dive into the atmosphere of Saturn. We're not allowed to keep it orbiting forever because it's not supposed to contaminate the Saturn system. So it will actually be controlled to dive into Saturn's atmosphere. In some ways that'll be a big relief to me because this mission has just been a fire hose of data that we have to keep up with all the time. And as much as I've enjoyed it, there should be an endpoint somewhere. Anyway, that's my talk. Thank you.
Thank you. Amazing.
Don, thank you so much. I really appreciate that. Do you have time for if there's a question or two?
Yeah, I've got my DVR running.
Why does the mission end in 17?
Well, the original mission, I should have said more about that. The original mission was 4 years, from 2004 to 2008.
Holy cow.
We have to negotiate for every extension. Cassini has been working almost flawlessly. Many missions, even if they have degradations, will be allowed to go on for a long time. But when you do that, it costs money and takes money away from other projects. And so a lot of times people want to get on to the next thing. But if you have something like this, Cassini's the only thing really going on out that far in the solar system right now. New Horizons, which I'm also working on, of course, will go by Pluto next year, and that'll be a big deal. But it's a flyby.
Can we get you back for that one?
It's possible, you can ask.
If funding was unlimited, what is the fuel supply like this? If it was-
Yeah, so we do most of our maneuvers without using any fuel. With just a little bit of a nudge, we can go high or low on Titan, and that changes the orbit completely. We do our rolling with reaction wheels, which are spun up using RTGs, radioisotopic thermoelectric generators. So they will go on for a very long time. Same kind of things that were used on Voyager. So we have the power. We probably will. The mission will end probably because we have to have enough fuel left to fly it into Saturn. So even though we'll still have some left at that point, we have to keep enough so that we can do that last part of the mission. Unfortunately, that's the rule.
Yes.
But we're actually been doing very well, and I shouldn't say it, but we probably could even go another couple of years if we had to. But we've decided that the solstice is a goal, and we've been very fortunate to be able to have the community, scientific and public, support us on that. We've had very high ratings scientifically all the way through, so right now it looks like we'll be allowed to do that.
Thank you.
Teresa?
Yeah, being an instrument geek that I am, what sort of detectors were you using in your IR instrument, and are they cryogenic?
Yeah, the instrument works at, the whole instrument's working at 170 degrees Kelvin. Main reason for that is you want to reduce the background because the hottest thing you're looking at is your instrument. So you cool as much as you can, and then you stabilize it well enough that it isn't changing between calibrations. There's one, the far infrared detector runs at that temperature, 170 degrees Kelvin. And it's a thermal pile, we call it, but it's really just a thermocouple. It's two thermocouples that are running in series, and it's a polarization interferometer. That's different than the one at Kidd Peak. It uses interference of polarization instead of splitting the light into amplitudes. But it's a similar thing, and in the mid-infrared, which is from 7 to 17 microns, we use mercury cadmium telluride. We use two arrays, 10 element linear arrays, one for each of those, one for each wave, a photoconductive array and a photovoltaic array, and each of those covers a slightly different wavelength range within. So the photovoltaic is going from 7 microns to 11 microns, sort of, 10 microns, and then from 10 microns out to 17 we use a photoconductor. So if you know something about infrared detectors, you're probably aware that that's sort of what you have to do to cover that range. And of course this technology may be 20 years old now, but people still come back and use it. I mean, it's some of the things were developed for our instrument we took a mechanism, a scanning mechanism, out of a display case a couple of years ago and got it working because some other project needed a scanning mechanism. It's amazing. Did that answer your question?
Yeah.
Any other questions? Well, I guess that gets to the end of our questions here, Don. Again, I truly appreciate this. Thank you so much. You're an honorary member of the Bear Valley Astronomical Society. Maybe we can send you a shirt.
That'd be great. Thank you very much. I really enjoyed it. It's great.
Okay, Don. Thanks again, and we'll let you get to bed.
Actually, I'd probably watch Sherlock Holmes or something.
Okay.
Okay, thank you, everybody.